Hello and welcome everyone to today's FAIRWork webinar. It is the 13th in our series, and today our colleagues from UNM Research, especially Dr. Lucas Paletta and Diplom Engineer Herwig Zeiner, will introduce you two parts of the FAIRWork project. One is how wearable biosensors can be used to compute resilience of workers to use in the decision making, and later on we will hear about optimization in this production environment, so how FAIRWork wants to achieve this. And if you are the first time here, we have more information about the context of the FAIRWork already in our webinars, which are the recordings available in YouTube, and this will also be recorded and put on YouTube. So, and then without further ado, I hand over to Lucas, who will start the webinar. Thank you.
Yeah, thank you very much, Christian, for the introduction, and welcome everyone to the first part of this talk, digital human factors analysis. And this digital human factors analytics is very much in the context of the framework of Industry 5.0, which is giving attention to the workers' well-being and fosters, therefore, a human-centric technology development. And one major focus is therefore to support the workers by building resilience on the workforce. And this digital human factors in this project is therefore on measuring the stress and resilience in order to avoid any toxic stress and to enable both human workers and decision makers to be more resilient overall. That means to be capable to respond appropriately if any short-term stressful work, for example, would arise. And these digital human factors analytics will be applied in two major use cases. Firstly, in the use case, as you can see, the workload balance or allocation that the project partner CRF, the research center of Stellantis, is interested in. Individual workers are here associated with, so to say, resilience scores that reflect the physiological strain of the workers, in particular with respect to intensive and long-term physical work. The physiological strain can be measured in terms of heart rate, skin temperature of the worker, and so on. Secondly, in the use case worker allocation that the other industrial project partner Flex is interested in, we measure here the cognitive emotional stress, the decision fatigue of decision makers working in front of the screen with various designs of decision support systems. This is measured using heart rate variability, skin temperature, attention scores, and so on. And finally, ethics and persona management are mandatory to apply human factors management in democratic AI-based decision processes. So for the FAIRWork project, we are focusing in the manner of explorative research on three different digital sensor technologies that are unobtrusive to some degree. Biosignal sensors, shirts, eye-tracking glasses, and smartwatches being equipped with high-quality biosignal sensors. The interpretation of the raw sensor data is applied within AI services that should be explainable, assuring fair, trustful, transparent operations. And finally, efficiently mapped to certain measures of cognitive and physiological strain, as well as effective and motivational state parameters. And we need these to relate to objective functions such as for stress reduction, consideration of well-being, safety, motivation, and so on. Finally, we will apply these functions to optimize the overall industrial processes. So we were now very curious about whether these wearable technologies would be accepted for daily use at the workplace, for a study, or even for a longer time. And for this reason, we presented the wearables to the workers and decision makers at the production site of Flex, Flextronics in Althofen, Austria, and asked them directly whether they would wear any of these technologies during work. As you can see in the upper diagram, the majority agreed to use the smartwatch and the shirt during long-term periods, whereas they rejected the glasses, but only due to the fact that we presented these jointly with an attached outwards orienting camera, but without that, they would agree as well. And so we actually don't need this urgently. So finally, high mental demand was reported, as you see in this lower diagram, as a daily load by many, preferably by decision makers. And bottom right, we report a highly useful discussion at the FAIRWork fair and workshop together with leads, decision makers, and workers at the other Flex factory in Timișoara, Romania, that provided additional clues on what to care about. We implemented the intelligent sensor box that is an architecture component with encapsulated data, collecting and analyzing services. And the purpose of it is to measure via sensors that are attached primarily to the human, as well as to the workplace, but keeping the privacy of the data. And only anonymous data are transferred to the overall system's knowledge base for further processing. We implemented in this first stage of the project the following intelligent services: the AI-based physiological strain estimation, as well as a first heuristic version of the cognitive emotional strain estimation. Further, a resilience score computation and an expert and developer dashboard for monitoring the raw and metadata in fact over time, the interface to the knowledge base, and a concept for persona clustering. Inside the intelligent sensor box, we implemented a support module seen to the left with the communication handler and the engine for a research and development dashboard. The raw signals are then grabbed, filtered, and forwarded to two major processing streams. One, seen in the right box on top, is related to the risk stratification for physiological strain, providing a strain index and a rule base to determine the risk level and recommendations on pause management. The second one, to the bottom now, is related to the cognitive emotional strain, again with risk level management. Now, central focus is on the resilience score that is delivered to the project's decision support system architecture. Resilient is on long-term stress effects and basically characterize the response behavior on stressful stimuli. Long-term stress and resilience have further consequences on production activity to the positive correlation with errors and periods of distraction at work, reducing the quality and performance of the worker and leading to new costs and losses for companies, also given by the corresponding increase of sick leaves and absenteeism. Now we apply the variables within two environments. Firstly, in an explorative manner at the human factors lab to the left. Secondly, we aim to apply them at the manufacturing site at Stellantis, Mirafiori, probably in autumn this year, depending on the confirmation by ethical approval. So our model for stress and resilience factors extends several previously defined models, such as the transactional model of stress and coping cited to the bottom right. The function of our model is designed as follows. The task demands generate strain in the worker that we measure by means of physiological strain, PSI star, as well as its cognitive emotional strain, CES. The long-term stress of both types would increase a mental exhaustion or the need for recovery, which in turn has a substantial impact on the overall psychological resilience. However, it can be empowered by the contribution of specific resources and finally impacts the coping capacity. Any recovery will eventually reduce the need for recovery and could be measured by its sleep features, for example. And in this sense, our model goes clearly beyond related work by using variable biosignal data and scientifically grounded strain scores, as well as computing resilience scores. Let's have quickly a closer look into the background of computing the resilience score. We determined a daily strain score by integrating contributions both from physiological as well as from cognitive emotional strain and apply a sigmoid saturation function. In the next step, we assign a time window in which we consider all the daily stress measures would definitely contribute to the impact of the state of that day that follows this time window, and in terms of impacting the dimension of the need for recovery on that next subsequent day. And contributions in this time window are weighted by recency, discriminating between long-term and short-term effects on the need for recovery. And finally, the resilience score must correlate indirectly with the need for recovery. And in addition, the input of additional resources physiologically, mentally, might add to resilience, and with this adds to the capacity of coping with new stressful situations. Now, the Human Factors Lab here at Joanneum Research, in which we intend to run the exploratory studies, provides numerous opportunities to study the impact on human factors in human-machine interaction, using the various digital sensor technologies and the cognitive computing services. This is often with the goal to provide a real-time assessment and feedback of it. And from this, to be able to shape the design of the technologies in the direction of intuitive human-machine interaction. Now we will watch a video with a demonstration of biosignal wearables to measure strain in the Human Factors Lab. Here are eye tracking glasses from Pupil Labs with front camera for egocentric scene videos and eye tracking from infrared eye-oriented cameras. The cable from the glasses leads to a smartphone that collects the raw data and sends them to the research server for analysis. The smartphone can be conveniently attached to the body. Now, the Garmin smartwatch is a highly unobtrusive wearable providing biosignal sensor data about cardiovascular information and psychological resilience. The Q Smart Shred textile also provides cardiovascular information from fibers leading to a Bluetooth hub that you can see connected via smartphone to the internet. And for a more precise computation of physiological strain, the so-called core sensor from GreenTech, skin temperature sensor, is required, can be easily attached to the body. So our colleague is now, in terms of a test person in the lab during the baseline measurement that could be taken early in the morning or at a quiet place where you pause. To the left, you can see the expert and the developer dashboard for the monitoring of vital signals as well as the physiological strain index. Seemingly during baseline, all these values are within the lowest range. Later, during an activity that now incorporates a dynamic load, lifting up and putting down 2 times 20 kilogram dumbbells at the same time, and the values are now increasing over time. On the table to the left is, by the way, a novel textile strap-based sensor device that nowadays replaces the shirt and is more comfortable. Meanwhile, with consistently ongoing dynamic load, the physiological strain index has continuously increased. Therefore, the risk level entered the yellow zone that you can see, and recommendations for taking rest and hydration actions have been triggered. This altogether is considered an interface for the decision support system. Now here we can see in the top diagram the raw data, such as heart rate in red, respiration rate in blue, as well as metadata in real time. Here the physiological strain index PSI in green. The mid diagram shows physiologically defined short and midterm risk levels in traffic light visualization. We can see that the PSI risk level, that's the bottom line of this mid window, turned to yellow to alert. The lowest diagram displays the triggering of recommendations, for example, to rest or to increase hydration through liquid supply, such as taking a bottle of water. Here we see a video of the scene camera with the eye gaze overlaid, the orange point. Eye tracking glasses are used in explorative studies, and the extracted eye movement features would soon provide more information on stress and cognitive emotional processes. The resilience monitor captures for each worker stress profiles within a time window of 20 days. Red, physiological strain, blue, cognitive emotional strain. Green below the resilience score, and the tendency goes towards higher resilience. Now the data of the lab session representing the day-to-day is uploaded, and as a result, the stress jumps high to the right, but the resilience course fairly reacts due to its inbuilt inertia model. Finally, the latest data are uploaded to the knowledge base for further decision-making, such as on the work allocation. Now, for the computation of physiological strain represented by PSI from wearable sensors, a key issue is to estimate core body temperature very well. Our approach for this was to use existing study data from trained professionals, including data about gold standard wearable sensors, as well as ground truth data of core body temperature from gastrointestinal pills in cooperation with the University of León in Spain. We computed the regression between skin sensor data and core body temperature and compared 26 kernel-based machine learning methods, and Gaussian progression regression, or GPR, clearly outperformed other methods, including neural networks and trees. The GPR is also available in an explainable AI version with local explanation, which reveals the feature contributions to the prediction of each sample, while maintaining at the same time the predictive performance of the GPR. In addition, one could consider GPR variants that could predict strain in the future. The two curves in the top diagram demonstrate the difference between core body temperature in blue and the GPR estimate in red, with a very small deviation. In the middle, the difference between ground truth and estimated physiological strain for a linear regression model to the left and the GPR-based model to the right is sketched. The table at the bottom gives a detailed account on the error measures to characterize the performance of the linear versus the GPR-based model. And the valid data that is outlined here are those data underlying the GPR model and that predominantly excluded outliers. Yes, human factors have a significant impact on the human decision-making performance. So cognitive emotional stress has a critical impact on the decision quality. Under stress, intuitive and therefore often suboptimal decision-making is preferred, and tunnel-like attention predominates. And the information overload and the decision fatigue significantly decrease the joint human-machine system performance. In first explorative studies with cognitive emotional strain, we applied a sequence of 3 tasks. To the left, a baseline session without substantial activity. Central column, a stimulus reaction choice task called determination test. And to the right, a task that is known to challenge cognitive load. That is the NBAC task that requires excellent short-term memory to appropriately react in time to a sequence of images presented to the operator. And this working memory task is here analyzed with an operator video to the left, being synchronized with the video of the egocentric camera oriented towards the screen with the gaze visualization in real time. You can see it, the green point. And to the right, real-time raw data output of skin temperature, heart rate, eye tracking based cognitive load score, with a resulting metadata stream represented by a so far heuristic index for cognitive emotional strain. And below again, the synchronized risk stratification in the traffic light representation. This is just ongoing work, and to investigate in more detail the detection of high cognitive emotional strain of the human decision maker by means of eye movement features using the eye tracking classes that you've seen before. And here are a few examples from ongoing exploratory research for indicating sessions of high cognitive emotional strain. So for example, firstly, high cognitive load and concentration goes with extended fixation duration, small saccade amplitude, and together with pupil dilation. And secondly, excessive multi-orientation stimuli go with high saccade rate and also high saccade amplitude. But we'll also take additional features like blink rate and pupil diameter in concern. As a next step in our work, the scores for physiological, cognitive, emotional, and affective scores representing the digital shadow, so to say, of the humans, will be associated with specific task context and further result, which is sketched here, in machine learning-based clustering with respect to persona representations, such as for aged experts or for young rookies. And these should then be related to decision-making that could lead to actions and adaptations in the overall socio-technical system. In this sense, we will develop human digital twins that can be used as operable and transparent representations of the human decision makers and workers under the consideration of course, all necessary ethical conditions. In the remainder of the project, we will tackle the following challenges and developments. In the next step, we'll have a wearable biosignal study at the production site at Stellantis called Myra Fiore production site in Torino. And based on these studies, we will be able to refine and finalize the FAIRWork resilience risk stratification service. A major attempt will be, of course, to apply fairness and transparent methods in order to enable responsible use of AI. And we will also cooperate on the optimization of workforce assignment. And for more details, I would like to hand over to my colleague, Herwig Zeiner.
Thank you, Lukas. So I will talk a little bit about optimization in decision support system and link it to the work what you heard now from Lukas. Next slide. First of all, I would like to say, because when we do this, what Lucas have shown, and when we use it afterwards in optimization service, it's very important that you think about it. What is the process? What exactly and how can decision-making process can be optimized? And how can you handle the resources in a proper way? We had a lot about the resilience now from Lucas. What can be useful then in your process? So first of all, this is the first step. Optimization goal definition, and afterwards it's important that you define a model. Or maybe your model can be divided into sub-models and you link it in a workflow. The human factors, as we heard now from Lucas, is very important here. And then when you optimize something, it's always important how much time you have to make the decision, how much time you have to calculate it, or how much time you have for the algorithms. And it's also important to implement it. Next slide. I just want to give you some short examples what we do currently and where resources, where persons are involved. First of all, we have here a problem where we bring things from one place A to one place B. Here you have clearly optimization objectives. So normally you have several. So first of all, you want to minimize the transport completion time. So you have this time-aware aspect. Then you want to maximize the worker satisfaction. So it's important that you consider, for example, the workload and the resilience of a worker, because this has an influence overall if he is satisfied with the overall work situation. And then another aspect is fairness. If you point several workers to a job, it's always important that at the end they have the feeling that they do similar workload over time and nobody is discriminated, so to speak. Then when you tackle such optimization problem, it's also important what kind of resources you have and which constraints you have. Here, when you bring things from A to B, you have some vehicles, you have maybe some time constraints regarding the locations. The system needs to be reliable overall, and you have maybe fixed schedules or maybe some dynamic schedules, so transport from which come into the plan, which was not planned before. And you need to also consider breakdowns, for example, of vehicles, etc., because or not availability of humans, etc. And then you have normally to solve this type of problems, you have a clear schedule for task jobs which bring things from A to B. You have to consider also here the layout of the factory and the logistic, if this is a factory. Then normally regarding resources, you have always a human put to one vehicle, and a vehicle can transport different types of things. And then it's also important that the transport is also in line with the time constraints of the overall production form. So you need to check if the transport can carry out in this available time, etc. And then you make the assignment to the transport, and the vehicle can schedule it in this aspect. Next slide. Another example, but to make it now shorter, is when you have a reallocation of work. Here could be also some differentiate can be from the optimization objectives here to minimize vacancy of lines. The other thing is very similar, so I don't want to go in much detail here. So therefore, Lucas, please, next slide. What is important here from every type of problems, what kind of selection of method you apply. This is a next important step. So please, Lucas, next slide. And here we apply an optimization different type of problems. I show you here another example where this optimization and this human factors may a role. Where I said before, Beside the transport problems, we have other problems in FAIRWorks. For example, you have some test process that you want to minimize usually search time for similar products or issues. Think in a simple error database. People working on a line, and then they put in some errors and they want to improve want to find in an effective way similar problems and to learn out, and you want to reduce the time what is available. So for this problem, we have here checking here similar stuff. We considering text here, we considering images of an error, and we considering maybe later videos. What we want to do is find very fast similar either errors or maybe project to carry out the maintenance. Next slide. As I said before, you have different type of modalities and you want to do it very fast and more or less. You can do it either with different service for each method, like text, video, etc. If you have different resources, or you put everything in the same resource and then use maybe a vector data bank where you search in a very fast way. In principle, for the problem, what is the critical issue from a user point of view, you want to find very similar projects, but maybe also are not so similar, but could be helpful for the workers to reduce the work, etc. And in all these use cases, what I've shown here, it's very important that you consider the stress of the workers, because in the long run, from a component perspective, you need to consider this because industry have less workers available and they want to do their job in a good way and in a less stressful way in the future. Next slide. So to come to an end, when you implement something like these 3 outlined use cases, you need to evaluate it here. And next slide, please, Lucas. So in principle, it's always important that you have objectives and then you measure at the end if you fulfill the objective or not. For the first type of problems, we consider normally these are optimization scheduling problems. We consider the computation complexity of the problems and check if it is possible the worst case running times of algorithms and compare it when we know it the best way, and then we know where we are here and how we fulfill it at the end. For the second type of use case, what I described you, we just consider the time to reduce for searching overall and to the time where the workers can learn faster because they find similar problems faster and solve the issue in a shorter time. So next slide. Overall, as a next step, we will implement this currently in the implementation phase on these 3 services. And hereby we use this workload resilience was shown by Lucas wherever it is possible. Next slide. And here you see also an overview of some of our publications related to this topic in our context. Now I give back to Christian to summarize up the seminar.
So thank you very much to our 2 presenters. And of course, if you have any questions, maybe we start them now. Do you have any questions? And otherwise, you have seen now the contact information. If you come later, you can, of course, contact us or the colleagues from UNM Research directly. Thank you very much. Have a nice day and see you soon. Bye.
Bye.
Bye.